Hello, everybody. Here in the third part of the lecture on solutions, we try to see the relative lowering of vapor pressure, which is one of the colligative properties. There are three more to be discussed in different sections. So part 4, 5, and 6 coming up later. Here we discuss the vapor pressure over the surface of pure solvent. You can see that this depicts the collection of molecules here. The three layers of molecules depict the first three layers of a liquid surface, which is made up of pure solvent. Molecules from surface are free to escape into the space above, creating the vapor pressure. It can be measured by using a manometer. In part B of the same diagram, you can see that the surface of the liquid is occupied by some non-volatile particles from a non-volatile solute dissolved in it. And therefore, blocking the surface to a certain extent creates a lower vapor pressure here because fewer molecules escape into the space provided. Therefore, the difference between the vapor pressure observed here and measured over here will have a difference. This will be higher and this will be lower. So the difference in vapor pressure can be calculated by minusing this or subtracting the vapor pressure here of the solution from that of pure solvent here. Now let us go towards quantifying these quantities. You can see the liquid attached to this manometer. This is manometer, and this is mercury filled in the two arms of manometer. The pure liquid molecules force the vapor pressure created by them forces the liquid in the left arm to go below, and a subsequent and equal rise is seen in the right arm. The difference between these two levels is the vapor pressure of the liquid here. Now, if I add some solute, this difference will get lowered. So this is how the measurement takes place. Now let the vapor pressure of pure solvent at a given pressure be P0S, and that of a solution containing a non-volatile solute be PS. It is not solution, it is solute. It should be read as solute rather than solution. BPS. The decrease in vapor pressure then is P0S minus PS, and it is represented as del P. Relative lowering of vapor pressure. It is not the vapor pressure or difference in vapor pressure which is colligative property. It is the relative lowering of vapor pressure which is the colligative property. And that is represented by P0S minus PS, or difference in pressure of pure solvent and solution, and divided by the vapor pressure of pure solvent. Now Raoult's law comes into play here, and it states that for a solution containing a non-volatile solute, again here we have solute, the relative lowering of vapor pressure equals to the mole fraction of the solute dissolved in the solution. The mole fraction of solute is represented by this italics X, Greek letter X, and subscript B. where Xb is the mole fraction of solute and Xa is represents the mole fraction of the solvent. Xa is given by number of moles of Xb given by number of moles of B, the mole fraction of solute, number of moles of solute divided by total number of moles of solvent and solute. And similarly, mole fraction of solvent is number of moles of solvent divided by total number of moles present in the solution of solvent and solute. Now, if we add them up, we get mole fraction of solvent plus mole fraction of solute equals 1. So, mole fraction of solute can be represented in terms of mole fraction of solvent also. It will be 1 minus mole fraction of solvent. Now, we have seen from the previous video that P0 minus Ps divided by P0s relative lowering of vapor pressure equals mole fraction of solute. But Xb we have seen is number of moles of solute divided by total number of moles of solvent and solute in the solution. Therefore, we can substitute for Xb its value in terms of number of moles. That's mole fraction. In a dilute solution, the number of moles of solute is far less as compared to the number of moles of solvent and hence can be neglected in the denominator. So the equation becomes P0 minus Ps divided by P0s is equals Nb by Na. Now Nb is weight of solute divided by molecular weight of solute. Similarly, number of moles of solvent equals weight of solvent divided by moles of solvent. Now, a molecular mass of solvent. This is molecular mass of solute. This is molecular mass of solvent. So, substituting the value of Nb and Na, we get P0 minus Ps divided by P0s equals weight of solute multiplied by molecular weight of solvent divided by molecular weight of solute multiplied by weight of solvent. From here, by transposition, Mb can be calculated by the relative lowering of vapor pressure method. And this is the equation. So if we transpose Mb on the left side, bringing all these unknowns on the right side, we get this equation. Molecular weight of solute equals P0s into weight of solute multiplied by molecular weight of solvent divided by the product of difference of vapor pressure between the pure solvent and the vapor pressure of solution multiplied by weight of solvent taken. I hope this serves the purpose and makes the things clear. And in the next part, that's part 4, I will discuss elevation in boiling point and how to calculate the molecular weight of solute from it. Thank you for watching. Do like, subscribe, and please feel free to ask any questions based on this. I will be more than glad to reply to all of them. Thank you and have a nice time.